Okay, it's 5:35. We'll get started now. So, hi everyone, I'm Julian. I'm a third year data science student, and I'm one of the education directors here at DataSoc. So, today we'll just be going through a revision workshop for Data1001. So, the agenda for today, so we'll be going through statistics, computer science, and business. So, the kind of the core three topics of the course, and at the end, Q&A and review to kind of go through what we've missed or anything else you want to cover, sorry. And of course, there's the attendance form on the right there, and it should be in the chat. So if you can fill that out, that would be great. So moving on, I'll hand it over to Adrian to get started on the statistics section.
Hi everyone, I'm Adrian. I'll pop my share screen on. Yep, I'm Adrian and I'll be running through the statistics section. Okay, so first off we have set operations. We first have the negation and complements. The easy way to remember this is to think of it as anything but a certain event. So in this case, that event is A, and we can visualize this on a Venn diagram like so. The next two are quite similar, intersection and union. We can think of intersection as event A and event B occurring simultaneously, and union would be that on top of event A occurring on its own and event B occurring on its own. So this is what the intersection would look like on a Venn diagram, and this is what the union would look like on a Venn diagram. Next, we have independence. This just means that an event can occur regardless if another event occurs or not. So they're independent of each other. And finally, we have mutually exclusive. This just means that the events don't occur simultaneously, so they can't occur at the same time. And on a Venn diagram, this is represented by two disjoint circles. Moving on, we have probability fundamentals. These are some properties that you should be familiar with, the joint, marginal, and conditional probabilities, and the corresponding formulas for them. We'll now get started with a question. I'll give you all about 10 seconds for this, and you guys can pop your answers in the chat. Yep, an answer from Johan, C, looks good. A, yeah, maybe. All right, let's go through how we might do this. Okay, so first thing is we want to see the probability of someone being male and believing that the dress was blue or blue and black, right? So what that might look like. Oops, yep, what that might look like is they have to be male and blue and black, right? So if we line that up, that's this cell here. So we want to figure out what X is. And because we know the total number of males is 49, we know that X plus 10 is equal to 49. And from that, we can deduce that X is 39. And then from there, we can calculate that probability. Let's try this next example. And again, 10 seconds for this. Pop your answers in the chat. Okay, Johan thinks C again. Yep, we're getting some answers in. All right. This one's also pretty simple. Probability that the person is a female. So we can kind of look at the probability of them being female and believing that it was blue and black and also white and gold, or we can just look at the total and see 51 out of 100, that's 51%. Okay, so the answer is also C. Moving on, a slightly harder question, so give a bit more time for this one. And this one relies on the conditional probability. So it might be useful to refer to the formulas on the left. But again, it's good practice if you don't actually rely on it. Alyssa says D, Aiden says D. Okay, we're getting some answers now. Yeah, that's right. This is how you might do it. So we're just using this formula here on the left. and we're lining it up with what information we have from the table, right? So the probability that they believe it's white and gold and they are female, so white and gold and female, we've lined that up. That's 19 on 100, right? And then for the probability that they're female, we did that in the previous part, so we know that's 51 on 100. And then we can calculate it's approximately 37%. So if you've got D, that's correct. Next section, we have Bayes' theorem and diagnostic testing. Diagnostic testing relies on Bayes' theorem. So we'll warm up with a Bayes' theorem question. And this formula will be right here for you to refer to. But again, it's better if you can do it from memory and not have to rely on looking at the formula on the table. So have a go at this one. Might take a bit of time to list the information out. But when you're ready, pop your answer in the chat. And with these kind of lengthier questions, it's important to know what we're trying to figure out. And then from that, we can look at the question to see, okay, what information do we have? Okay, so Zach says D. Wait for a few more answers before I move on. Yeah, Amy says D as well. All right, let's look at the working out for this. So from the very last sentence of this question, we want to figure out something, right? So what is the probability that it was manufactured in factory A if a random light bulb turns out to be defective? And the way you read this probability, A given like a certain event, right? That's the way you want to phrase the question. And then you put that into Bayes' formula. And then now we have a bunch of things that we need to figure out, like probability of A, the probability that it's defective given A. And then we look back to the question and then we can find all of this information out. Once we have all these values, we just plug them into the formula and we can figure out that the answer is 3 on 7. All right. Now let's move on to a diagnostic testing question. So this kind of ties everything together. So you might have to refer to some stuff that I mentioned in the set operations slides. So have a go at this one. It might take a bit more time. You might have to refer to the table a bit more if you're not familiar with sensitivity and specificity. And since this one isn't multiple choice, you can put your answer to 3 significant figures in the chat. Okay, let's move on to the answers. So the thing we're looking for is the PVP, or the predictive value positive. And that's what that is, right? So if we look from this table, the PVP is the probability that they are diseased given they tested positive, right? So that's what we look for. And then we just plug that into Bayes' theorem again. And then we have expressions that or values that we need to look for. And then from the question, we know that sensitivity and specificity, we know what the probabilities are or how to represent them. And then we can, I guess, list out all our information here. Now we look for what we're missing, right? So we have this, we have the probability that they have the disease. So we're missing pretty much these two values at the bottom, right? In the numerator, or in the denominator, sorry. And that is the probability of D complement and the probability of T given D complement. And because they're very easy complements, we can find that just with the negation formula in the first few slides, right? So we find that very easily. And now we have all the values again, just like in the previous Bayes theorem example, to actually sub it in. And subbing it in, we have the probability of disease given they tested positive to be 62.3% approximately. Okay. All right. And what does this actually mean? So how do we interpret this? So from here, the PVP, it means that they are diseased given tested positive. So we're finding a probability that they have the disease given they tested positive. So in simple English terms, that just means that there is a 62.3% chance that a patient will have the disease given that they tested positive. And in this case, this disease is COVID-19. So another chance to practice this time we're looking for the PVN or the predictive value negative. And because we did the question in part 1, we can reuse some of the information we figured out or that we listed out. So we do less working out. And if you need the formulas, bring that back up. But we're looking for the PVN, okay? And once you have your answer, just pop it in the chat. All right, so for this question, for the PVN, it's very similar steps to what we did for the PVP. So we know what we're looking for because of the formula. We list out our information, and if we need to, we calculate any other missing values to sub into Bayes' theorem. So we do those exact same steps. This is what we're looking for. That's a Bayes' theorem. And then we list out the information we know. Some of this information we obtained in part 1. And then we just need to find the missing information, which is this last value here. We do the complement, sub that into whatever formula we have, and we approximate 99.9%. Moving on, we have the types of variables. And this is just a bit of theory. This is an easy way to kind of visualize and lay out the types of variables that you can encounter. We have qualitative and quantitative that branch out into 2 separate sections. We have nominal, where things are unordered. So if you think of colors like red, green, blue, these don't really have an order to them. But for ordinal, they do have an order. So if you think of your grades like A, B, C, D, there's like a natural order to that. For quantitative, we have discrete and continuous. Discrete would be like age or stuff that you can count on your fingers, right? So integers. For continuous, it's like measurable. So you can think of it as sort of like a slider, right? So if you slide along something, you can select any value on that slider, and it might be like 1.1. So those have decimals. Those wouldn't be discrete. And within the quantitative section, we have a scale, so ratio and interval scales. For the ratio, the 0 is significant. So if you think of a length, when you have 0 length or 0 centimeters, for example, that means there's a complete absence of whatever length you're measuring, right? But in the interval example, or for temperature, which is an example of interval, the 0 is arbitrary, right? So 0 degrees, that's a bit arbitrary. You can go into the negatives as well. That pretty much captures all the types of variables. I'll now hand over to Noah to talk more about random variables.
Thank you very much. So, hi guys, I'm Noah. I'm Education Co-Director here at DataSoc, and I'll be taking the rest of the stats section as well as some art coding later. So, stay in tune for that. So I'll show you the rest of the slides. So yeah, so just picking up where Adrian left off, where we have discrete and continuous random variables. Here are some like formal mathematical definitions. So everything on the left column here applies to discrete random variables, and everything on the right compares to continuous random variables. And what you're going to notice here is the summations that you see in discrete often just turn into integrals for continuous. Now, this slide is mostly just here for completeness. This course doesn't require you to compute any integrals of any kind, but it will be useful in courses like Math 1B. So we see here that a lot of the summations that we see in the discrete case just convert to integral in the continuous case. One thing that they'll ask you questions on in the exam is the binomial distribution. And what this is used for is when there is a clear success and a failure. So we'll see an example later, but here's just like the binomial distribution, sort of like your one-page summary. We have a few assumptions about the binomial distribution, so we can only apply all of these formulas that you're seeing on screen if we have something called independent trials. So the outcome for like your current trial isn't influenced by what happened previously. We also need two possibilities, like a success and a failure, like a binary sort of outcome. And once we know these sort of things, as well as some other things that I'll go into soon, we can use all of the formulas that you're seeing on screen. And there's going to be a question that covers all of this, but just here's your one-page summary if you wanted it. Cool. So here's a question, and just to drop a hint, we are going to be using the binomial distribution, and you'll see why. So the question here goes, in a large restaurant, an average of 3 out of every 5 customers ask for water with their meal. A random sample of 10 customers is selected. Find the probability that exactly 6 ask for water with their meal. So I guess the case here is just working out what your n is, what your x is from the previous slide. So it's just a case of working out what's your n, what's your p, and what's your x. That's my hint. Okay, so I'll give about 30 seconds for that, just to whack it into your calculator if you want, but we'll go through the answers after. So what we'll see here is that we can express the answer just like this. So from a few slides back, we do n choose x. Just keep in mind that a few slides back, it was defined in terms of factorials, but you can also enter your n choose x sort of notation as well. So from 10 customers, we are choosing 6. The probability that a customer asks for water with their meal is 3/5. So that was your p. We raise that to the power of x, which corresponds to there as per the formula. And then you take 1 minus the probability times to the power of n minus x. So this is nothing but the formula that you saw a few slides ago, just with our n, p, and x all subbed in. If you put this into your calculator, or if you're really with it, you can use R to calculate this, and you'll see that you get 0.25 to 2 decimal places. Now, the second question asks us to find the probability that less than 9 people ask for water with their meal. So what we could do is we could, find the probability that 0 people ask for water with their meal, plus the probability that 1 person, asks for order their meal plus a probability of 2 people plus a probability of 3 people plus 4 and so on up until 9. But the problem is that becomes quite like expensive computationally. I mean, at least to just do it by a calculator. So what we can do is we can appeal to complementary probability. So we can do 1 minus the probability of the opposite thing happening. So if we want to find the probability that less than 9 people ask for their water with their meal, we can do 1 minus the probability that more than or equal to 9. And that's exactly what we're doing here. So you'll see that the probability that x is greater than 9, greater than or equal to 9 is the probability that x equals 9, as well as the case where the probability that x is equal to 10. And if you're wondering why I haven't done 11, 12, and so on, a random sample of 10 customers is selected. So we have to like chop it off there. And the probability that x equals 9 has its own formula, which you're seeing on screen over there. And the probability that x equals 10, of course, has its own formula. So we sub that in to the next line. Evaluating that all onto your calculator, you're going to get 0.95 to 2 decimal places. Just keep in mind, you might have to evaluate it to 3 decimal places, 4 decimal places, 2 decimal places. You're just seeing it here, but you might just always keep in mind what the exam is asking. Cool. Okay. One thing that you would have seen from that 1-page summary from the binomial distribution is that we can calculate these things called expectations. So E of x, which you can think of as like the mean, the variance, so like var x, which you can think of sigma squared as the variance, and then standard deviation, which is nothing but the square root of the variance. And so all that we have to do is take a look at this question. So suppose a large factory produces candy bars at scale. Though at this factory, 2% of the bars are defective, a quality check involves randomly selecting and testing 500 bars. What is the mean, variance, and standard deviation of the number of defective bars in these samples? So what I've done here is I've actually just clearly defined what our random variable x is. It is the number of defective candy bars. That's like our random variable x denotes that quantity there. We know it's a binomial random variable because it fits this 4 criteria. And so once we know it's a binomial random variable, we can apply all the formulas that apply to the binomial distribution. Okay. So from a few slides back, you would have seen that the expectation of our random variable is nothing but n times the probability of success. Now, in our case, the success is the fact that the candy bar is defective. But just, yeah, keep in mind, that is our p, so 2% or 2 over 100. And so what we do is we take our sample size n and we multiply it by the probability that a candy bar is defective. And so what we can say is that the mean of our random variable x is 10. The variance is calculated sort of in similar fashion. So you're seeing the NP that you see for the above formula, but the thing that we have to add is 1 minus p, so the probability of the complement happening. So the probability that the bar is not defective. So what we see here is n, our sample size of 500, times the probability of the bar being defective, times the probability of it not being defective. And putting that in your calculator, you get 9.8. And if you look at the standard deviation, that is just the square root of the variance. So your answer is just going to be whatever the square root of 9.8 is. Okay. One other thing that you're going to need to know is the Poisson distribution. So the Poisson distribution is often used to model count data. So if we're modeling like the number of events per particular time period. And so it's defined in terms of this parameter, which we call lambda. And in questions, it's just a case of identifying what lambda is. And once you know what lambda is, you sub it into your expectation of x formula, your variance formula, and then you can also find the probability that your random variable x is equal to a particular value, little x. But you'll see how this all goes together in the example now. So in a village, power cuts occur randomly at a rate of 3 per year. So power cuts, the event of a power cut happens 3 times per year. So we know that we're going to need to use the Poisson distribution. And so what we now do is we find the probability that in any given year, there'll be exactly 7 power cuts. Okay. So what's happening here is the rate, which we call lambda, is 3 because the power cuts happen 3 times per year. So that's your lambda. And once you have that lambda, you can sub it into all of your expectation, variance, probability formulas. So the probability of exactly 7 power cuts is just subbing in lambda equals to 3 and x equals to 7. So you would have seen that the formula was defined in terms of E Euler's constant, lambda, as well as the x factorial on the denominator. But all I've done here is I've just subbed in x is equal to 7, lambda is equal to 3, as per the information from the question. The probability of at least 4 cuts, we can appeal to complementary probability again. So that's what we see over here. So if we find the probability that in any year there'll be at least 4 cuts, we can do 1 minus the probability that there was 0 cuts, plus 1 cut, plus 2 cuts, plus 3 cuts, using complementary probability. And what you're seeing here is that we can do it in 2 different ways. There actually is a third way, but just to avoid confusion, I've just to keep things simple, I've outlined 2 ways in which you can calculate this quantity in R. So in the first example, we are summing the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability that x equals 2 plus the probability that x is 3. And you're doing the exact same thing with PIS, but instead of using this long-winded thing here, all you have to do is specify a Q value of 3. And it'll do the same thing. Just notice here that the lambda, you have to specify your lambda because Poisson variables are defined in terms of lambda. Lovely. We now move on to the normal distribution, which is a continuous random variable. So unlike Poisson and binomial, which is a discrete random variable, the normal distribution is continuous. So you're seeing here that it can take on any values within a continuum. Here's what we call the density of a normal random variable. It's not anything that you'll need to remember, but I think just for completeness, here it is. And when we saw that with the binomial distribution, it was defined in terms of n being our sample size and p being the probability of success. And we saw that Poisson distributions were defined in terms of lambda, but with the normal distribution, we have this quantity called mu and sigma squared, where all that mu does is, if you just look at the diagram, as we shift mu across, the distribution sort of just shifts across like that. And as we increase the variance, or as we increase the standard deviation sigma, of course, the square of the standard deviation, the variance will also increase. So you see that larger values of sigma are correspond to a distribution that's more spread out. So I guess in the case where sigma is 2, the green one here, it's the most spread out of all of the distributions. So mu calculates the shift across, and sigma squared calculates how spread out it is. Okay. One important thing to note is that the normal distribution is symmetric. So if you chop it in half at the maximum, 50% of the area would be on one side and 50% of the area would be on another side. Sometimes they call it a bell curve. So that's why, because it's bell shaped. And it's also unimodal. So it only has one maximum, and that maximum is the mode, which is actually also the mean, which is the median as well. If you're wondering where the R section was, I know there was a little bit of R code in the second part of the Poisson question, but for more in-depth data analysis in R, we're actually going to do that after the computer science section, once we've gone over all the computer science theory, and then you'll sort of see some R code after that. And the script for that will be uploading as well for everyone who's turned up here. Lovely. So I'm going to pass it on to Lily now, who's going to cover computer science, and it's going to be shared between us too. So we'll alternate between us, but I'll let her take over now.
Thanks, Noah. So I'm Lily, and I'm going to be presenting the computer science section of the revision workshop. Firstly, we're going to be discussing binary search trees. So binary search trees are a data structure which store different values and data in a structure that you can see on the screen. They are better than just storing data in a list or something, because when you have massive sets of data, that can be pretty inefficient in terms of searching, inserting, and deleting. And binary search trees are a great alternative. So now just going through some important terminology, subtrees. So at the top in this example, 5 is our top level main node. The left subtree is all of the values on the left of 5, and the right subtree is all of the values on the right. An important characteristic of the left subtree is that they will always be less than the main node. So as you can see, 1, 2, 3 are all less than 5. And similarly, for the right tree, all of the values are greater than the main node. So 9, 12, 19, 21, 25 are all greater than 5. So now we're moving on to parent nodes and child nodes. So the parent node is on the level above and connected to a node, and the child node is on the level below and connected to a node. So it's better to look at this when we're thinking of a specific example. So over here, we can see that 25 is the child node of 21, and 21 is the parent node of 25. This is similar when we move up a level. 21 is the child node of 12, and 12 is the parent node of 21. Again, 12 is now the child node of 5, and 5 is the parent node of 12. And these terms apply to all combinations of nodes in the tree, which are connected in a similar way. Leaf nodes. So the nodes that are on the bottom level of the tree, which have no children. Here we have 1, 3, 9, 19, and 25. These are called leaf nodes. Unlike all the other nodes, 2, 5, 12, 21, which have children, these ones don't have any, so we call them leaf nodes. So what can we do with binary search trees? One very important thing we need to know how to do is search for values. So for this example, we're going to try find 19 in the tree. We start at 5, and then if the node's value is less than the value we're searching for, we look in the left subtree. If the value we're searching for is greater than the node's value, we search the right subtree. So we're going to try find 19. We look at 5, 19 is greater than 5, so we move to 12. 19 is greater than 12, so we move down to the right subtree. And as we can see, 19 is less, so we move left, and that's where it is. Another important thing we need to know how to do with binary search trees is inserting a value. To do this, we firstly need to find the appropriate position using the search method that we did in the previous slide. We need to then create the node, and then you have your new binary search tree. So for now, we're going to try inserting 4. So we're going to start at the top node at 5. 4 is less than 5, so it would belong in the left subtree where we reach 2. But 4 is greater than 2, so it would belong in the right subtree. We reach 3. 4 is greater than 3, so it belongs in the right subtree. There's no more nodes over here, so we just create the new node 4, and that's where it belongs. An important thing to consider when inserting nodes is that sometimes the appearance of a binary search tree might be slightly different based on the order different nodes are inserted in. If you're looking at the binary search tree we have here, we can just pretend for now, if 4 was inserted before 3, 4 would actually be over here, and then 3 would be over down here on its left subtree. Just something important to note. So now we're going to move on to another thing we can do with binary search trees, which is removing nodes. There's 3 cases we need to consider, and there's slightly different procedures as to how we'll go about removing nodes. So firstly, if there's no children in the node we want to remove, 1 child or 2 children. Start at the easiest one, no children. We simply remove the node and there's no adjustments we need to make. So over here, we're going to try delete 18 from this binary search tree. We can see we've got it down here. It's a leaf node with no children. And to remove it, we simply delete it. Second situation, if the node has 1 child, we want to delete the node, and then in its position, we put its child node. So over here, we're going to try delete 25. As you can see, it's got 1 node on its right subtree. To delete it, we need to remove it. and then in its position, because at the moment 30 is just floating randomly, we need to move 30 up to where 25 was. And you can see the new binary search tree on the right. Now, this is the trickiest one. If the node has 2 children, we need to firstly delete the node. And then to ensure that everything remains in the correct position in terms of everything on the right being greater, everything on the left being lesser, the rightmost node in the left subtree has to take its place. So this will make a bit more sense once we've looked at the example. Over here, we're going to try delete 20. And you can see the outcome. So we've deleted 20 by putting the rightmost node 19 in its position. 19 is the greatest value in the left subtree, which means that 19's new left subtree, which is 20's old left subtree, everything will still be lesser than it, and everything on the right is still going to be greater than it because it was greater than 20, and the binary search tree is still correct. I'm going to pass over back to Noah, who will discuss decision trees.
So yeah, with decision trees are another part of your syllabus that you guys cover in the comp sci section. They're used extensively in things like machine learning, if you go deeper into that field, and then the basis for much more sophisticated tree algorithms. But for now, let's just take a look at how a decision tree works. Essentially, it's nothing but a whole lot of fancy if this, go that way, otherwise or else go to the right. So what you're seeing here is just a sort of a concrete example. What you're seeing, the salary at least 50,000. So if the salary is at least 50,000, go left. If not, go right and decline the job offer. And then what we see is that there's all of these fancy, if this, go that way, otherwise go that way. And what we can do is make decisions based off what our tree structure is telling us. The way in which we actually build this tree is through things like entropy and information gain. There are some other criteria that you can use, but the ones that you guys get taught is 1, entropy, and 2, how we can use entropy to then compute information gain. And that will tell you which variables you should be splitting on for your trees and what values of those variables, in this case, 50,000, but for what values of those variables should you split on, okay? So we have this concept called entropy, which is a measure of sort of randomness in the data set. And we want to minimize, we want to be able to make very clear splits. We want to be very confident in our splits. So let's say we have a response variable y, so y being the thing that we're trying to predict, and let x1 be, maybe is sunny. So 1 for is sunny and no for is not. And then x2, you can use your imagination for it to be any sort of binary feature. And what we want to do is we want to try predict y. We want to try build a tree that can model y and make good predictions. Okay. So the first question asks us to find the entropy of our variable y in the data set below. So here's our data set, and we want to find the entropy of this y column. Don't worry, we've got a formula. So you saw in the previous slide that we call entropy, you can call it h of x. In this case, it's going to be h of y, or you could write it as just entropy. But the way in which we compute it is we take this quantity called pi, which is the probability that it belongs to a particular class, and then we times it by the log in base 2 of that probability. So in our case, if we want to find the entropy of this y column, we have to find the probability that y is equal to 1. So we have 1, 2, 3, 4, 5 out of a total of 10 values in which y is 1. And so that's where the half comes from. The probability that y is 0 is there's 5 values in which y equals 0 over a total of 10. So that's a half. And the entropy, or h of y, they call it, is basically you just take the probability that y is 1 times the log probability plus the probability that y is 0 times the log probability. And I've just taken the minus out the front because if you think about it, you could just take that minus outside of the summation and nothing changes. And so what you see here is that the entropy is 1. So if they say find the entropy of this column, that's how you do it. They're also going to ask you something called the information gain, where it's the information gain in itself that is actually used at the end of the day to make these splits that you saw in the original slide. So the way in which we calculate information gain is to take the entropy of the parent node, which we've already calculated, h of y, and then what we do is we subtract a weighted average of the entropy of the child nodes, which you can think of as the conditional entropy. I'm going to go through each calculation here, so don't be too scared by these formulas. So we already have hy in our formula. So we know from before that hy was equal to 1 because of the calculations on the previous slide, using the formula that had the log in base 2 and all of that. What we now wish to find in blue is the probability, or the entropy, given that x1 is equal to 1. So what we're doing is we're sort of filtering down all the values in which x1 is equal to 1. So I've labeled it in blue there just to make it very clear. So what we do is we calculate the entropy, but only considering the blue cases. So what we get is the probability that y is equal to 1, which is 3 on 6, times the log of that 3 on 6 probability, and then we plus the probability that y is 0, which is 3 on 6. 3 out of 6 of them was 0, times the log 2 of that probability again. We can do the same for the pink examples. So using the exact same formula, you'll notice that there are only 4 pink examples. So that being x1 is equal to 0. And what you see here is using the conditional entropy here, plugging everything into the formula, you get 1 again. So once we've computed all of these child entropies, we combine it into what we call information gain. So if we go back to where it says hint, we see that the information gain is the original entropy that we calculated, h of y, which was 1 in black, minus, in the square brackets, observe how we've taken the blue and the pink and we've popped it into our formula here, but because we're taking a weighted average in the green, we're scaling it by the amount of the proportion of blue and the proportion of pink. So we see that the proportion of blue was 6 blues out of a total of 10. And we see that the proportion of those that were pink, so x1 was equal to 0, was 4 out of 10. And so that's where those green multiples are coming from there. And we see that the information gain from splitting on x1 is going to be 0. If we repeat the process for x2, we see that you go through all of your computations again. And what I've actually done here is I've actually just crossed off the x1 column because we're not interested in x1. We've now shifted our attention to x2. And what we can do is we can calculate both of the conditional entropies. So the entropy of y only considering the cases in which x2 was 1. And then we can calculate the entropy of y only considering the cases in which x2 was 0. And again, we plug each of these conditional entropies into our information gain formula, and we scale it by the green, which is 5 over 10, because there were 5 over 10 of them were blue and 5 over 10 of them were pink. Okay, this might take one extra read through of the slides, because especially if the section was covered maybe a few weeks ago, so maybe you just need to rehash your knowledge a bit, but really take some time to observe how these calculations were actually made and where the 5 over 10 in green and the 5 over 10 came from. What you're going to notice is once you put all of this into your calculator, you get an information gain of 0.2781, which was bigger than the last one of 0. And so what we do is we notice that information gain can be thought of as the decrease in entropy after splitting over a variable. So we want to be able to gain lots of information about our data set once we make splits. So the information gain being higher means that we have a more favorable split. So choosing x2 to split on is the best option, i.e. it's better than splitting on x1 because it has a higher information gain. We can extract more from our data set from making that split. So that's what you're seeing highlighted in orange. And we can build this tree as deep as we want. In practice, you can set how deep you actually want to build the tree. And I guess the main thing that I'm trying to allude to here is that this algorithm, you guys will only have to run it on like very small data sets using like, hand calculations. But the thing with decision trees, and in particular, the ID3 algorithm, is that it can scale to much more columns and much more rows of data. You can have an arbitrary amount of columns and an arbitrary amount of rows, and it's all happening computationally. But just for now, all that you guys need to know is how to do it on a small data set and just understanding how entropy and information gain is calculated, using the data set that you've got. Okay. Cool. And so here's another example of a decision tree. In this case, we are, modeling the data set shown on the previous slide. Cool. Yeah, I'll pass it back on to Lily, who's going to cover balloon filters, and then to finish off the comp sci section, I'm going to do some R coding as well, and I'll pass on to her now.
Thanks, Noah. So we're going to continue with the computer science section now, doing some balloon filters. So balloon filters are a space-efficient probabilistic data set. So what they are is basically if you have a massive data set, which would take up a lot of space and time looking for elements in it when we're trying to use them, balloon filters are a great way to, I guess, sort of test whether an element is probably in there or probably not, using much less space and time. The only downside to it is it doesn't have 100% certainty. So as we will discuss later, there are chances of getting false positives when we're retrieving data. So how they work is we have hash functions, which you can see over here. And when we insert an item into the filter, we basically work through each of the hash functions and set each of the indexes, which are initially initialized to 0, meaning negative, to 1, which means positive. This will make a bit more sense after an example, which we'll go through now. So for this example, we want to initialize an empty balloon filter given the following hash functions and entries. So the first hash is simply the length, mod 5. The second hash, that should be a 2 there, is the first letter corresponding to the value, so A1, B2, so on, mod 5. Here is our empty filter. Entry indexes 0, 1, 2, 3, 4, all initialized to 0. And this question is asking us to insert edu and data. So firstly, with edu, we'll look at the first hash function. The length is 3, mod 5 is 3 still. So we simply want to set 3 to 1, as you can see here. Now we'll look at the second hash. The first letter is E, so if we're counting A, B, C, D, E, E is the fifth letter, mod 5 is 0, so we set 0 to 1. So that's the first data entry done. Now we're going to move on to data. Length 4, which means that we set 4 to positive, and the first letter is D, which is the fourth letter in the alphabet. Mod 5 still 4, but because we have already got 4 sets of positive, we just leave it as is. So this is a fully initialized balloon filter, and we can, if we're trying to test if a element is in a set or not, we would simply run the hashes on the element we're testing, and if it comes back positive for all of them, we can say that there is a chance that there is. Now, we have a little question. Which of the following is impossible for a balloon filter retrieval? Retrieving an element that is indexed in the array and not in the set. So according to the balloon filter, it is there, but it's not actually in the set. Indexed in the array, but not in the set. So it's in the array, but not actually in the set. Not indexed in the array and in the set, or not indexed in the array and not in the set. If you just want to pop your answers into the chat, that would be great. I'll give you a minute or so. Okay, so the answer is C, not indexed in the array and in the set. So this is impossible because if it isn't in the set, we would have already hashed all the appropriate values when we were initializing the filter. So it's impossible for us to retrieve that. So now thinking about another thing, we're going back to the example before, and we're going to be discussing false positives. So although it doesn't happen all the time, there is a chance that when we are testing if an element is in the set, even though it isn't actually in the set, according to the filter, it is. So over here, we're going to look at the entry, just the word egg, so EGG. If we're testing if it's in the set, we're going to test both hashes. So length 3 mod 5, positive. So this is for the word egg still. First letter is E, fifth letter mod 5 is 0. So according to the hash filter, to the Bloom filter, the element might be in the set, but as we know, this is the set, so it's not actually there. So here's a little summary of Bloom filters, which you might want to read through in your own time, going back through the slides. We've pretty much been through everything, so I'll just move on for now. So graph representation. So a graph is a collection of nodes connected through edges, sort of similar to what you can see on the left side of this slide. It's kind of hard to put this into just a computer or data structure just through the visual way it is. So we need ways to store graphs in computers. The first way we're going to discuss is an adjacency matrix, which is something like you can see over here. So it's a matrix of size n by n, if the graph has n nodes, and the values are 0 if the nodes are not connected, and 1 if they are. So looking at the example we have here, V0 is not connected to itself, so it's set to 0, but V0 is connected to V1. So this value is set to 1. As you can see here, V0 is connected to V2, so that's 1. And it's also connected to 3, so that is 1 as well. So we've initialized most of this adjacency matrix appropriately, but there's 2 values, X and Y, that we have not. So if you want to just think about what they should be and pop your answers in the chat, that would be great. Okay, let's see what the answers are. Oh, sorry, must have missed that bit. Just give me a second. Okay, so V1 and V2 are connected, so that should be 1. X is 1, and V3 is not connected to itself, so it's just 0. I can see a few of you got that right, so well done. Another way of representing graphs is through an adjacency list. Now, you might be thinking, why would we use one or the other? There are various benefits when it comes to searching, insertion, deletion, but we're not going to discuss those now. And it's just good to know what each of them are. So in an adjacency list, for each node, we have a list of the other nodes it's connected to. So for each node over here, we just have a list of the nodes it's connected to. So 0 is connected to 1, 2, 3, 1 is connected to 0, 2, 2 is connected to 0 and 1, and V3 is just connected to 0. It's a pretty simple way to represent a graph. And yeah. So now that we've discussed how we can sort of represent graphs, we're going to be discussing breadth first search, or BFS, and depth first search traversals of graphs. So we've got the example that we're going to be working with on the right over here. And you don't need to write out your answers or anything, but if you just want to have a little think of what a breadth first search would look like and what a DFS search would look like of this graph whilst we're discussing the answers. So firstly, the breadth first search. So we want to explore all the nodes at a given depth before moving on to the next level and exploring those nodes. In order to do this, we use a queue data structure so that once we've moved on to one node, we can still come back to the other without losing track of where we are. So the aim is to visit the oldest unvisited vertices along the edges in the beginning, and we're using a first in, first out approach. If you want to try visualize this to think about it better, think of a water ripple extending in an outwards direction. So we're looking at all the things that are in a certain distance, and then once we've done that, we'll do the next distance and so on and so on. So over here, we're starting at the source, which is 0. We want to firstly explore all the nodes that are connected directly to 0, which are 1 and 2, which means that once we've explored those, they'll be added to the queue so we can come back to them. Next, we're going to move on to looking at the nodes that are connected to 1, because that's at the beginning of the queue. But as you can see, that is just 0 and 2, which we have already explored. So that's done. Now we're going to move on to 2, which is at the same level as 1 still. We explored the nodes that are connected to 2, which are 3 and 6, and 0 and 1, but we've already done those, so we can disregard that. So as you can see, we've done the source node and we've done both of its connections. So we're now moving on to the next level. As you can see, we have queued 3 and 6 as well, and we're going to start by exploring 3. So we're checking 3, and then we need to add its connections to the queue. That's only 2 and 4. We've already done 2, so we just add 4. Now 6 is on the same level as 3, so we'll explore that now, but its only connections are done. So we move on to what is now at the end of the queue, which is 4. And 4's only not visited connection is 5. So then we'll do that next. So as you can see, we sort of went through the nodes that are connected directly to the source, and then the nodes that are connected with 1 in between to the source, which were 3 and 6, 2 in between, which was 4, and then the last one, 5. So now a DFS. It's a different way of traversing a graph, but instead of going as wide as possible, we sort of kind of want to go down each individual path as far as possible before coming back to the alternate paths. We're going to use a stack data structure for finding this path, and we're focusing on visiting vertices along the edge in the beginning, and we're using the first in last out approach. Another way you can visualize this is by exploring a maze and hitting a dead end before backtracking. So going as far as you can in the search, and then only when you can't go any further do you come back. So going through what the DFS for this graph would look like, we're going to be starting at the source, and its two connections are 1 and 2. So we're going to start with the lowest one, which is 1, and explore as far as we can get just looking at 1. So we start at 1. 1 is also connected to 2, so we can go there. 2 is connected to 3, so we can go there. 3 is connected to 4, so we can go there. 4 is connected to 5, so we can go there. And now we've hit a dead end. So what do we do here? We backtrack until we find another path we can explore. So we go back to 4. We can't go anywhere from there because remembering this is a directed graph. Go back to 3, can't go anywhere from there. Back to 2. Now we do see another path that we can take that we didn't explore yet, which is just going to 6, and then we've explored the whole graph. And you can see down here that is the stack structure that we use to explore the graph. Here is a really great way just to visualize what each of these searches would look like. If you want to come back and read through the slides, this is a great way to remember. Okay, now moving on to K-core. So a K-core is a subgraph of a graph where each node has at least K neighbors, and K can be any value you want, and you're normally given it, and you'd have to try to find the K-core of a graph. So over here in this little circle, this is a 2 core because all of the nodes in here have at least 2 neighbors. You can see F is E and G, G has many, and E has C, G, and F. So this is a 2-core. A type of K-core is a maximal K-core, which basically means that in the entire graph, all of the nodes have at least K neighbors. So you might be asked to try to find the maximal K-core in an exam, so it's really important that you know how to create it. So the operation we use is recursively deleting nodes from a neighbor, so its degree is 1. A has 1, 2, 3, so its degree is 3, and so on and so on. So we're going to start at the smallest degree and remove the nodes and the edges if it is less than K. And then, so just say we were trying to find the maximal 3-core. From this graph, we would be removing F and I because that's less than 3, and therefore they're not going to be a part of it. But once we've done that, for example, if we remove F, A will have 1 less connection, so degree will become 2. So we need to keep doing this process until all of the nodes in the graph have a degree greater than or equal to K. So that's the computer science section done. I'm just going to pass on to Julian, who will do the next part of the presentation.
Yeah, thanks, Lily. So we'll have a short little break now. Just before we do that, we'd just like to grab a quick photo quickly. So if everyone can turn on their camera, if you're willing to do that, we can get a quick photo, and then we'll have a short 5-minute break. So I'll give everyone 5 seconds or so if they want to turn their camera on. Otherwise, I'll just snap the photo. Oh, good. Yeah, if your camera isn't working, all right. You don't want to turn it on, it's all good. Okay, we'll give it 5 seconds or so. Okay, we're looking good. Okay, I'll count down from 5. 5, 4, 3, 2, 1. Yeah, I got it. Thanks, everyone. So I'll put up the slides again quickly. Okay, so from here, basically, we'll have a short 5-minute break, and then we'll continue with the R section from here. So if you want to ask any questions now, it would be the time to put that in the chat. Or if you just want to get up and stretch your legs, that's also fine. So yeah, we'll come back in 5 minutes. So for the time being, yeah, putting questions in the chat if you have any. So sorry, Richard, for the weighted part, could you elaborate more on that? Sorry. Was that with the computer science part? Oh, that would be the difference between mean and expected value. Yeah, got it. Got it. Adrian, did you want to handle that? Otherwise, I'm happy to.
I don't mind. Yeah, no, so basically you can think of it as like a long-term average. You can Yeah, so it's basically like it's like a generalization of a weighted average. And I know that doesn't really help because you were wondering, well, what the weighted average is. But I encourage you to actually look into the slides, my very first slide on random variables. And you saw that for a discrete random variable, you take the particular value and then the times it by the probability of that particular value, and you sum it over all of the possible values that your distribution can take on. So yeah, I guess just to sum it up, think of it as like a long-term average. I don't know if that helps anymore, but that's, I guess, my explanation.
Another one for you, Noah, I think. And yeah, Richard, yeah, it's a bit of a technical sort of definition issue, but yeah, definitely look it up as well. That's also a good one. Yeah, you'll definitely be spending heaps of time reading about that, but I wouldn't dwell on it too much. But if it helps you understand, go for it. But Noah, there's another one for you on the ID3 method. Do you see that one?
Yeah. To make a split, you have to recalculate. You recalculate the information gain given that the stuff above it has happened. So if you're like way down in a tree, you recalculate the information gain, but you only consider the rows in which the split has allowed you to like traverse down the tree. So like, for example, if you've already made a split based off like, you know, a variable being less than 37, like age being less than 37, we recalculate and we want to, you know, traverse the left subtree. We recalculate the information gain, but we only take the rows in which x is less than 37, if that makes any sense. So you recalculate,
but you're only considering the rows such that the above conditions are true. Oh no, it happens recursively. So it's almost like you restart. So the conditions from the node above have to be true, but you still do a greedy search over all of your variables. So it's not a case of, there is actually the random forest algorithm, which only considers like a random subset of the variables. But for decision trees, you're recalculating the information gain, considering all of the variables again. The only thing that changes as you move down the tree is that the above conditions have to be true, of course. We're done.
With the Bloom filters question, I'll just go through that quickly. So it is impossible to retrieve an element. It's impossible to retrieve an element that is not indexed in the array and in the set. So basically what that means is that if it's in the set, if it's in the set, it's 100% going to be indexed. So it's impossible for an element to be not indexed in the array, but actually in the set, because just when we set it up, that makes it impossible. Hope that makes a bit more sense. If not, the summary slide at the end should help.
Lily, I think your mic dropped for like 2 seconds, but if we want to go through that again later, at the end, and that's, yeah, we can do that. But I think for the moment, it might be better to move on. And also feel free to explain it in the chat as well. That might be useful. You can definitely elaborate a bit more there. But for the moment, time keeps going, so we have to move on, unfortunately. So hopefully everyone is back and refreshed, and I'll hand it over to Noah to go through data wrangling in R. So all yours, Noah.
Thanks, guys. Sweet. So basically this R script aims to cover everything that you guys did in weeks 1 to 3, or whenever your stats section was. So yeah, I mean, here's just a summary, and we'll go through each part of the code and what it does, but you'll actually see that once I explain one particular thing, the rest will sort of fall into place quite naturally. But let's actually get started. So when doing data analysis in R, one very, very popular package to use is something called tidyverse. And with tidyverse, we can do all of the sophisticated data analysis operations that R allows you to do. And so if you haven't actually, if for whatever reason you haven't used R yet and you want to like quickly cram, you're going to need to install .packages tidyverse. And what this line will do is it will install this package called tidyverse. And what tidyverse does is it opens you up to a world of sophisticated operations that you can run on your data. So once you've loaded up tidyverse, we're going to use the library function, which loads in the tidyverse package. So if you're coming from Python, this would be like import whatever your library is. Now what we're going to do is we're going to read in our data, and we're going to use the read.csv function. And what read.csv does is it reads in a CSV file. And this CSV file is located at this URL, which I've linked in the chat. So if you are following along with a blank R script, you can use read.csv and paste in this URL. So once we have that, we can import our data. And what I'm going to do here is I'm just going to take a look at what the first 5 rows of our data looks like. So it's actually a TikTok data set. And we're looking at the popularity of particular TikTok songs. So you see here that we have the artist name. We have a whole lot of variables like the popularity out of 100, I believe. And then we have all these interesting metrics like how danceable it was, the energy metric, the loudness, and all these other variables here. And we're going to see how we can do some data analysis on this data set using some R operations that dplyr gives us access to. Okay. So all that we did there is in another tab, we looked at the first 5 rows of the data, like the head of the data. We can get all descriptive statistics over here. So what you're seeing here is that we can get, for each variable, we can get the mean, the maximum, the minimum, and other information like that. And you'll see that if you scroll, you see all of your variables here. So artist name, popularity. And so, for example, the maximum popularity was 100 and the minimum popularity for a TikTok song was 0. Okay. We can get all the column names as well as the rows and columns in our data set. So we're dealing with 6,746 rows of data and 21 columns. With this tidyverse package, we get access to our other R packages such as dplyr, which you might have heard of. You would have probably seen it in one of the labs. But library tidyverse, it allows you to use all of those packages at the same time. So when analyzing data, R allows us to run 5 very special functions. Now, there's so many more, but these are probably the 5 most important, at least when getting started with data analysis in R. And we're going to give an example of how each one can be used when analyzing our TikTok data set. Okay. So the first one is select. And what we want to do is just pick off a few columns. We can pick off one column, we can pick off a few of them. And the most important thing that you can see from this is this % greater than % symbol here, which we call the forward pipe operator in R. And wherever you see this, the only thing that you must do is just replace that with and then. Okay. So wherever you see this, just think and then. So in this example, we'll take our data and then select just the artist name and the genre column. So if we run that, we get just the artist name and just the genre. And I can scroll up here and we get all of the artist names and all of the genres, every single row in the data set. Okay. Artist name and genre. We can negate this by using the minus, and anytime we're collecting, a few columns together, we're like putting a few columns together, it's nice to use this C function, which you can group things together with. So in this case, we want to take our data and then select all the columns apart from artist name and genre. And this will give you all the columns apart from the artist name and the genre. So what we see here is that we get, that might be a little bit too much to scroll through, but we get all of the columns except for the artist name and the genre. You can take my word for that. So that's how we negate. We have this thing called filter where we can subset particular rows. So for example, maybe we only want to look at songs that had a popularity of greater than 80 or something like that. So in this example, we take our data and then filter such that the popularity is greater than 80 and the duration minutes is less than 3. So we want songs that were higher than 80 in popularity and were less than 3 minutes in length. Once we've done that, then select popularity and duration mins. Okay. And what you're seeing here is that if I was to scroll up, all of these popularity values would be greater than 80. And the duration minutes would be less than 3. Now, if you're wondering what these numbers on the left are, these are just the row numbers. So this would be row 356 in your data set. But this is the popularity and this is the duration. Cool. And you might notice there that we use the AND operator there using ampersand. So you wouldn't write AND, you would write ampersand if you want to do AND. It's very similar for OR. So instead of OR, you just do a vertical bar. And in this case, we want to take our data and then filter only rows in which the popularity is 20 or Katy Perry, or the artist name is Katy Perry. So either the popularity has to be less than 20 or the artist name has to be Katy Perry or both. And then once we've done that, we're going to select popularity, artist name, and liveness. And so you see, it becomes pretty effortless once you think of this forward pipe as and then, or just then. So take our data, then filter, then select. Okay. Cool. And let me actually just view this and we can get a better idea of what's happening. So you see that we only get the popularity, artist name, and the liveness, and we extract all the ones in which the popularity is less than 20, or the artist name was Katy Perry. Okay. So there's Katy Perry. The popularity is greater than 20 though, but it was Katy Perry, so it still qualifies as a row to look at. We then have this function called mutate, where all that mutate does is allows you to create new columns. And a lot of the time we're going to be creating new columns from existing ones. So I guess in this example, what we've done is we have our data, then we're going to mutate. And what we're going to do is we're going to create a new column called duration hours. And the way in which we plan on creating that column is by taking the duration mins column that we already have in our data set and dividing it by 60, since there are 60 minutes in an hour. Okay. And so that's what we have there. So we have an intention to create a new column called duration hours, and the way in which we create it is using that formula. Okay. Cool. And now we have a duration hours column. Okay. We then have this thing called summarize, where we can use it for aggregation functions. So we'll take our data and then summarize. And what do we want to summarize? Well, let's take a look at the average song length. So we can create this column average duration, which is simply the average of the duration minutes. And then we can create a median liveness as the median of the liveness column. And so what you get here is some output that will tell you both the average duration and the median liveness. Okay. There's also group by. So with group by, we want to, for each, you can think of group by as for each. So take our data and then for each artist name, get the mean popularity and sort it in descending order. And that's what you're seeing there. And so on average, it was these artists that had the highest average popularity. Okay. We don't have too much time left. I did want to allocate only 15 minutes for the R section. So we've got about 4 minutes left, but I'll show you how we can now visualize our data. So those are the 5 important words: select, filter, mutate, summarize, and group by. And now we're going to look at how we can visualize some of our data. So we now have a new data set called Star Wars, and this is just built into R. So if you just type in Star Wars, it loads in the Star Wars data set, and we can take a look at the first 5 rows of this data set using the view function aforementioned earlier. Okay. In this case, we want to create a box plot. And so the code that we can use to create that is this. So basically what we want to do is we want to create a box plot, and by gender, we want to see how the heights sort of vary. So what you're seeing in the right graph is that there seems to be more spread for the heights of individuals in the Star Wars dataset, and all of the rest of the things are just basically plot settings. So your Y label, your X label, main is just the title, LAS rotates the Y labels, and we can specify the colors as a vector because we have 2 genders in this dataset, and we can specify the colors if you want to. So what we can now do is we can do a scatter plot, and we can use a scatter plot to compare a continuous variable to a continuous variable. So in this case, we're comparing heights to mass. So we're seeing the relationship that exists between heights and mass. This code over here is just more of more detail as how we can label our title, how we can make it bigger, how we can change our X labeling. So what I encourage you to do in your own time is just to really experiment with these numbers and sort of see what happens. So let's see what happens if I change this to 3, and you'll see how the plot changes. You see that it became italicized. Okay. The next thing that we want to do is with our Star Wars dataset, we want to see if there's actually a correlation between the mass and the height of individuals. Now, what I'm going to do just first, before I actually look at that, is I'm going to delete this observation because it's clearly an outlier. It's clearly very different from the rest of them. So just for the sake of looking at the correlation between mass and height, so i.e. whether they have like a linear sort of relationship, we can actually just delete this variable. And we're just going to use some deployer stuff that I went into earlier. So we're going to create a new data set, which is going to be taken by filtering our old one such that the mass is less than 500. With this new data set, we can use plot functionality like we did before, but one thing that tidyverse offers is something called ggplot. And what ggplot does is allow you to create really, really aesthetic looking plots. So what we see here is that we're taking our Star Wars new data set, and then we are creating a ggplot where we intend to put mass on the x-axis, height on the y-axis, and we tend to color the dots in terms of the gender. geom_point allows the dots to be added to the screen. ggtitle puts a title on it, and all that this theme thing is doing is just centering the text, making it bold and things like that. Okay. Now what we want to see is the strength of this linear relationship that exists between the mass and the height of particular Star Wars characters in the data set. So what I'm going to do is I'm just going to extract the mass column using some deployer magic like before. So we can extract just the mass column, and we can extract just the height column. And what we can do is using COR, we can find the correlation. And this is Pearson's correlation for anyone who's, a little bit more with it. So this is doing the correlation between the mass and the height of particular Star Wars. And what we can see is once we run that, we get a correlation of 0.76. And it's positive because, if you were to look at the linear relationship that I'm drawing with my mouse here, you see that it has a positive gradient. And the 0.76, the fact that it's very close to 1, or it's quite close to 1, implies quite a strong positive correlation. So we would say there's a strong positive correlation between mass and height. Okay. Now, there's not a whole lot left here. This is just a mosaic plot. It was used to create this following plot. I encourage you to go through that in your own time. Nothing really happening there. But yeah, that's the R section done. Just a quick and concise summary of how R can be used for data analysis. And at 14 minutes and 56, I think I'll end it there. So I'll pass it on to Julian, who's going to cover the business section now.
Yeah, thanks, Neil. And yeah, we'll share that code as well. We'll send that out in a pack too. So I'll just share my screen here. And hopefully you can see the presentation. Is that right now?
Yeah.
Yeah. Oh, thanks. Yeah, right. So we've gone through stats, computer science, and now we'll go through business. So I'll try to keep this brief enough so that we still have time for questions at the end. So to get started with business, first of all, we'll look at some types of data collection, and then we'll go into some problems with bias. Then we'll go into looking at some types of experiments, and then finally we'll go back into R and look at linear regression, logistic regression, and correlation versus causation. So to begin with, looking at types of data collection, as you probably know from high school, there's a few types. There's primary, secondary. There's also qualitative and quantitative. So primary being where data is collected directly from a source, and secondary being data collected by an individual who's not the original user. So that could be in the case where we get it from an ABS website, where we're not actually the Australian Bureau of Statistics, of course. And of course, there's also qualitative and quantitative, which I'm sure you're super familiar with. And then there's this question at the bottom here. So why do we need effective data collection methods? And I've got three listed here. So first being integrity of research, to reduce likelihood of error, and then finally, which allows for the identification of target consumers, which of course allows us to reduce costs. And some of these goes nicely into the second slide here, which talks about bias. And for context, usually in stats in general and in experiments, it's really inefficient to perform experiments and analyze the entire population. In fact, some would argue it's impossible because we can't analyze the entire population, even for a census. Some people might argue that the entire population encompasses all people in the future and in the past. It's a bit broad, but I've definitely heard some business lecturers argue that. So in this case, we actually want to take a sample that represents the population. And in this case, there can be some biases that arise from this. So the first being selection bias, which you've probably heard of, which is type bias that occurs when we take a non-random sample of the population. So I've got an example here. So this is when we call a landline to gauge which political party people are going to vote for. So in this case, we could be calling a specific state on purpose and not, for example, randomly sampling from multiple states around the country. There's also a similar type of bias, which is called self-selection bias, the second section here, which occurs if individuals are given the freedom to decide whether or not they want to participate in this study. So the example here is that we're going to take an online survey asking people about their preferred diet. And the problem is here that since it's online, any person can actually go on there and choose whether they want to take the survey. So in this case, you might get a lot of people that actually have a bias towards a specific diet, maybe a bias towards a specific diet, sorry. For example, people maybe on the keto diet might be super motivated to just share the good word of the keto diet, for example. So they might be super obliged to go into the survey and fill it out. So in that case, it might be how we introduce bias. So speaking of experiments, there might be two sort of general ways to collect data from experiments in a broad sense. And the two that you might have heard of being observational and experimental data. So observational data, the key is in the word in observation there. So the definition being where we observe relationships between explanatory and the response variables, where the researcher, us, is not in control of the response variable. So the problem with this is that it might not be super effective at determining causal relationships because we're not actually in control of the response variable, what we're actually trying to discover here. And as a result, there might be a very long research time required. So for example, if we don't have control, there might be if we don't have control over the research time, it could in fact be something quite long. Perhaps it's a policy, for example. The second type of data collection method there is experimental data. And this is sort of the classic where we assign a treatment to a group and observe changes in the response variable. So this is what you would normally encounter in your high school science, and even in the clinic, even in clinical trials. And this is generally much stronger than observational data with a much shorter research time, since we're actually in control of the amount of time we spend collecting the data. However, it can be expensive, since we actually need to perhaps pay people to actually be involved in our double-blind experiment, for example. So as I mentioned, these two methods are quite broad. So I'll go into a small little case study now, specifically a natural experiment, which is a type of way that we can collect observational data. So again, for context, so we talk about a natural experiment. It sounds very familiar to an observational, where we collect observational data. So it's an empirical study in which individuals are exposed to experimental or control conditions determined by nature. And again, similar to observational data, it's not actually within the control of the researchers. So let's look at an example here. So in this case, a smoking ban is imposed for 6 months in the Randwick LGA. And over the course of those 6 months, we see a 40% decrease in rates of heart attacks. And once the ban is lifted, the rate of heart attacks increases once again. So this is kind of key observational data here. So we have 6 months. So again, it's a really long time. And we don't have control over this. So it's something that policymakers might have put in, not exactly the researchers themselves. And in this case, yeah, as I said, we can only observe the changes before and after the policy change, but we can't actually decide, for example, which LGA receives the policy or what even type of policy they receive in the first place. So to kind of combine everything together, I'll go through a short question here. And this kind of encapsulates the type of problem that you might encounter in the final exam, or even that you might have encountered previously in one of your tutorials, where it's the style of question that asks, what are the problems with this experimental design? And some things to consider before we take a look is how do our variables interact with each other? And as well, how have outside factors, how will they affect the accuracy of our experiment that's being controlled for or uncontrolled for in the case of an observational design? So this comes from 2020 T2 week 9. So we've got our friend from Seinfeld here. And the question goes, Jenny Craig is a weight loss intervention. Their commercials show a photo of some celebrity before and after joining Jenny Craig. A, being, what are the control and treatment in this experiment? And B, are you worried about any selection problems? Please explain. So does anyone want to have a go at question A? I'll give maybe 5 seconds. So give me the control and the treatment in this experiment. Or B2. Okay, that's fine. Everyone must be getting pretty tired. It's getting late. So I'll go through A. So the control here is, of course, the weight before the treatment. And the actual treatment itself was joining Jenny Craig. So where in a sense, giving the participant the Jenny Craig program to see what happens. And B, are we worried about any selection problems? And the answer is yes. So Jenny Craig has control over who actually, over who they use in their ads. So they are actually likely to choose only success stories that are presumably more successful, which makes sense because Jenny Craig would never put in a failure in their ad because it doesn't look good and doesn't attract as many customers. So with that said, I'll now swap to the R section. So we've developed a R Shiny app, which is pretty much an interactive R app that we can go through. That'll go through linear regression, some real world examples and logistic regression, and finishing off with how correlation doesn't equal causation, if we have time, of course. So to begin with, as you probably have seen plenty of times now for the past few weeks, we've got the linear regression model here, the standard model. So I'll go through what each of these variables mean here. So yi, so the yi here on the left, that's the outcome or dependent variable. And I've subscripted it with data point I. So it's super important to remember that we have a bunch of data here. Next, we've got each beta here. So beta subscript p. So we've got p variables. And here, this means ceteris paribus, or all other things held equal. How does the dependent variable yi change if our independent variable xi changed? In that case, it changes a beta I amount. And intuitively, this means how important is variable xi in predicting yi. And we'll go through some examples about that later. And next, as we mentioned before, the independent variable xp. So here, in this case, we've got p input or dependent variables. And finally, we've got ui, which is our random error for the unexplained variation in yi. And intuitively, you can just think of this as the error term, which contains all the other variables that we haven't accounted for. And especially, we'd be especially careful about ui, since these extra variables could sometimes be correlated with our independent variables xp. I've also got an important note here that a linear model must be linear in parameters to be counted as a linear model. So in this case, you can quiz yourself by going to this quiz section and submitting your answer to see if you're right. I won't go through it now to spoil it, but it should be pretty obvious which one is linear in parameters, and hopefully you succeed there. So I'll move on to actually going through how we find the beta. So a little bit more technical. And we've got the technique here known as the sum of the squared residuals. And the goal here, minimize this formula, simply just being the yi, so our actual value, minus y hat I, which is our predicted value, and that all squared. So you can think of that as the difference. So how far off were we from the actual value that, from what we actually predicted? And this diagram sums it up quite nicely. And what linear regression really does is that it's just minimizing this distance or difference, you could say. So we can add some more questions about that, but I think it might be more important to move on to a real world example. So in this case, we're going to look at this data set called the CARS data set. So it's a pretty famous R data set. And of course, since it's super famous, they use miles per hour, unfortunately. So we're just going to have to live with that. And the two variables we'll be focusing on is going to be on speed and the numeric stopping distance dist here. And we can take a look at the data here. But let's say we will actually model this. So in this case, we're going to be using the LM command, so stands for linear model, to model this relationship. And we can do that by using this formula. So effectively, we can translate this into distance, which is y equals, we use this little tilde here to note a equals for our formulas specifically. And that's going to be speed, which is our only independent variable. And then we can call summary on that to give us a whole bunch of statistics about that, specifically being maybe the errors, the p-values, if you've heard of that, the intercept, and of course our coefficient here. And finally, we can go down to the bottom and we've plotted it. We can see a nice red line through our data with our R squared being the goodness of fit, as you may have heard, being 0.65. So I'll take a moment there to stop for a second and let you sort of take that in. So there's a lot of information here, but what we might want to focus on and what exam question might ask us specifically is to comment on the coefficient, for example. So they might say, how would you interpret this linear model? And we could say something like ceteris paribus for a 1 unit increase in the change of speed. We could be getting a improvement in about a 3.9 unit increase in sorry, I got that mixed up with a 1 unit increase in distance. You should be getting a 3 unit increase in speed. And with our R squared, with our goodness of fit, we are getting 0.65, which is fairly good, meaning you can say that's a fairly strong, I believe it should be a fairly strong relationship. I'm not sure exactly what the bounds they give you, but let's say if it was 0.1, you would say that's a very weak relationship. So I'll move on to this second concept here, which talks about adding higher terms to your model. So in this case, we've added a square term, so we call that a higher term. And now the new model is yi equals beta 0 plus beta 1 x squared plus ui. And we can do some calculus here and actually differentiate it to find the actual meaning, which is ceteris paribus. The marginal impact of increasing x1 by 1 unit results in a 2 times beta 1 unit increase in yi. So if you study this, you'll actually figure out why this is the case. I won't go into it too much for the moment, but we'll be sending this out and you can have a closer look, and by running the code more, you'll actually see that as well. So I'll move on to another important concept here, which is fairly common in the final exam. And I've summarized it pretty much in this table here by looking at transformations. So what we might want to do is the way we can actually transform our data is by taking transformations of the actual model itself. So in this case, we've got the first model here, which is a log level regression, which means that we are actually doing a log transformation of our dependent variable yi. And we've got the interpretation here, which means if we change xi by 1 unit, we'd expect a 100 beta 1% change in yi. So why is this actually the case? So as before, if we were to differentiate this model and we get the change, we'd find out that this would be the case, that would get this interpretation. And similarly with level log and log log. I'll let you explore that more, but it's quite an important topic, and you can most likely just get through the final exam with this table here as reference. So moving on, away from linear regression, there's also logistic regression that we have to look into. So from a high level perspective, what actually is logistic regression? How do we get to the formula you've seen before, which is this one down the bottom? So before we actually get to that, we have to first discuss what log odds are. And I've got the formula here. So for the probability of success P, we can look at the log odds, which is of course the log transform of odds. Odds being just the probability of success divided by the probability of failure. So simple as that. And then we do a log transformation of that. So what does this actually have to do with logistic regression? So if we equate our familiar linear regression. So we've got a simple linear model here with just one independent variable with our log odds. And we do some rearranging. We, funnily enough, end up at our familiar logistic regression here. So you can see that there's actually multiple different ways to interpret logistic regression. In one sense, we can actually interpret it and deconstruct it back to log odds. And I'll be looking at that for the interpretation. So once again, to find the interpretation, we actually need to differentiate this first formula here, which I'll let you do yourself if you want to learn about it more. But just knowing that this formula is involved can help you just understand this interpretation if I can read it out. So ceteris paribus, if we increase the predictor, so our beta, sorry, not our beta, our x by 1 unit, with that multiplies the odds. So our odds here, p1 minus p, so that multiplies the odds of the outcome, so our y, occurring by e to the beta. So this is, of course, assuming we have our coefficient beta. And again, you can prove this to yourself by finding the first derivative of the log odds regression model. So this formula here. So that's all complicated, but we can look at a real so-called example, and we'll take a look at that by predicting heart disease with smoking, which is a binary variable as a predictor. So if beta smoking equals 0.4, then we plug that into our formula. We see that that equals 0.6, which would imply that smokers have a 60% chance of getting heart disease. We could also plug that into our interpretation simply enough, and by saying e to 0.6, whatever that number is, would be our interpretation. So increasing the predictor by 1 unit multiplies the odds of getting heart disease by e to the 0.6. So again, that's a lot of information. So we'll probably go through just this last part of logistic regression, and then we'll end it there and we'll go to questions. So you've heard me talk about logistic regression, but we'll actually now use it in a real world example and compare it to linear regression. So I've got this maybe more complex data set here that looks at diabetes. So we've got a bunch of medical terms here, but at the end, we've got predicting onset diabetes. So between 0s and 1s here. So in this case, let's look at linear regression. And you can see that linear regression doesn't do a very good job of actually modeling this at all. If we take a look at what would happen at 25 here, so we're modeling here plasma glucose concentration against onset diabetes. If we looked at a plasma glucose concentration of 25, just notice how this red line would actually be negative here. And if you notice, we're actually trying to predict an onset diabetes between 0 and 1. So we're trying to predict a probability. And if you remember, the one thing you should know about probabilities is that it should always be bounded between 0 and 1. So it being negative is actually a huge red flag. And in that case, we should try a different technique. And of course, you might have guessed it, that we're actually going to use logistic regression. So I'm going to cheat here and use the solution just to speed things up. But I definitely would say that you should try to run this yourself and play with it a bit. And even to get the summary stats out of this. But just for this sort of demonstration right now, we can just see how logistic regression has solved our issue and has bounded our model between 0 and 1. So now we're actually getting and predicting onset diabetes between 0 and 1, and we've fixed that problem at 25. And of course, I can do the summary of logistic regression and get all of the additional coefficients as well, and the R squared, which wouldn't be very helpful here. But all of these things you can generate and have a look for yourself and try to use the previous interpretation here to try to work it out yourself. So with that said, we've got about 5 minutes now, so we'll move on and move to the Q&A and review. So just a short review before we go into the Q&A. So I've looked at 3 topics, of course. We've looked at statistics, so that included Bayes rule, set operations, probabilities and looking at a bunch of distributions. We've also looked at computer science, looking at binary search trees and a bunch of course, graphs, breadth first search, depth first search, and the representations of those. And finally, business. So econometrics, we've been looking at experimentation, and finally the interactive R part with linear regression and logistic regression. And to end things off, we've got a bit of time now just to go through some questions. So if anyone has anything they want to ask about, have anything clarified about those 3 sections, now would be the time. But other than that, that would be the end of this workshop. So while you're thinking of your questions and putting them in the chat, I'll just finish things off. So we've got resources here. We'll definitely send everyone who's filled out the attendance form the slides and a resource pack that you can go through that includes a final exam from 2 years ago, Term 2. And of course, you can take a look at DataSoc's previous workshops. So everyone who's sticking around for questions, you can stay and do so. But for everyone else, thanks for coming and hope to see you again. And please fill out the feedback form so we can help improve our future events. So thanks everyone. And yeah, if you want to stick around for questions, please do so.